we talked about kinetic molecular theory, we're going to move on to Boyle's law. Okay, so Boyle's law is the gas law that relates pressure and volume. Okay, so in this video we're going to talk about how pressure and volume relate, and lucky you, we're bringing back in the math. Alright, so know the relationship between volume and pressure. This is very important to know what that relationship is, and to first kind of show you that, I'm going to go back to that preparatory chemistry website and show you an animation for Boyle's law. So let me switch over to that right quick and we will get started on that. Alright, so this animation's pretty good. This apparatus on the right has a bunch of gas molecules in there. It's got a thermometer, it's got a piston that I can use to change the volume. If I move it down, then I'm decreasing my volume. It's got a thermometer to show you that the temperature is going to stay constant. So we're only talking about relating pressure and volume, so that means we have to keep those other factors that affect gases like number of moles and temperature constant. We have to make sure those stay the same. And there's also a pressure gauge right here on the side that's going to show you what happens as we change our volume, what happens to our pressure. Okay, so gas pressure, we've already talked about what that means in the kinetic molecular theory video, but basically it's just the collisions between those moving gas particles and the walls of your container, and we measure that by knowing the force of these collisions divided by basically how much surface area that I have for my walls. Okay, so like I said, there's four things that affect gases: volume and pressure, which we're talking about in this video, and also in there is the number of molecules or the number of particles, which is the number of mole, which we use the moles to measure. And as you can see, we're not going to have any leaks in this system, so we're going to be able to keep that constant. And also we're going to keep the external temperatures. We're not going to let those affect anything, so we're going to or the heat can flow in and out of the container, and because of that the temperature is going to remain constant. So when I click next, you're going to see the volume decrease. Okay, so when I decrease my volume, you're going to kind of see what happens. It's going to increase my number of particles, not the total number of particles, but just how much space those particles have to move in. Alright, they're going to have less space to move, so they're going to be more concentrated in that space. Alright, that's going to cause more collisions per second per area, and because of that there's more force per little area, and this means that there's an increase in gas pressure. So follow along with what happens when I click next. You're going to see us move the volume by lowering the piston right here, decreasing my volume in that way. So now I decrease my volume. Okay, so there's more, you can see that it's more concentrated in here, so I have more concentration of my gas particles per volume. Alright, that's going to increase the number of hits on the wall, so these particles are hitting my walls of my container a lot more often now. That's increasing the force of those collisions and therefore increasing my gas pressure. So because there are more hits per area, there is more pressure. Okay, so you can kind of follow this logical sequence here. As I decrease my volume, I'm increasing my number of gas particles per the container, and in the end I'm increasing the force of my hits and therefore increasing my gas pressure. It works the other way. Okay, so it works the other way. If I instead increase my volume, then my pressure is therefore going to decrease. So they're always going to go in opposite directions. One goes up, one goes down. One goes up, one goes down. One goes up, one goes down. Okay, so from there I'm going to go back to our presentation here, and I'm going to finish it off. Alright, so you want to know what type of relationship that you have. Okay, so when we're talking about what type of relationship, we're going to call this type of relationship inverse. Okay, so it's an inverse relationship, which means that if one of them goes up, so if my volume increases, the other's got to go down. So one increases, the other goes down. We're going to call that an inverse relationship. You know, likewise, the same thing. As my volume decreases, my pressure is going to increase. So they're always going to go the opposite of each other when we're talking about Boyle's law and volume and pressure. So that's something that you need to be able to do. You also want to be able to explain Boyle's law using KMT, kinetic molecular theory, and that's what you saw on that online animation as well. As I decreased my volume, my pressure went up because you saw more gases hitting the sides of the wall because they had less space or less volume to move in. Alright, so we're going to move on from that. Let me take off what we got there and move on to my first example problem. So we're going to do two example problems. They're very similar to the types of problems that you're probably going to see, so they're definitely beneficial for you. So I kind of broke this out into steps, okay? So I have my first step, and I'm going to call my first step what you have, or what you know. Okay, so let's talk about what we know. All right, we know that for Boyle's law problems that we're relating volume and pressure, okay, my formula, and I should have included this on a slide before, but I was kind of assuming you have your notes already. Your formula for Boyle's law is volume 1 times pressure 1 equals volume 2 times pressure 2. Okay, so we need to find these values to plug in. So that's going to be my first step, that what you know. Okay, so I'm going to move down to my question. The pressure of 12.3 liters of gas increases from 0.5 atmospheres to 570 millimeters of mercury. What is the final volume of the gas, assuming constant temperature? Okay, so I'm going to find what I know. I'm going to find pretty much my first number. Okay, in my last video, you probably saw me have a fit over units. If it says liters, what is that? Liters is a unit of volume, okay? So I want to move over and I'm going to use it as my first volume because it's the first number that I have. So I'm just going to say my first volume is 12.3 liters, okay? And then I'm going to kind of scan and see if I see any other times that I see volume in this problem. Well, it asks me what is the final volume. Okay, that final volume here, they don't give me a number. That's probably what they're going to want me to find. Okay, so they want me to find volume 2. Next, I am going to see if I can find my pressure 1. So my pressure 1 and my volume 1 are going to be under the same conditions. Okay, so as my volume is 12.3 liters of gas, I have a pressure of 0.5 atmospheres. So I'm going to write that down. That's my number there, that 0.5 atmospheres. Okay, and then under my second set of conditions, my second pressure, it says that it increases. My pressure increases, so it's changed to 570 millimeters of mercury. And that's my first step, finding out what I know. All right, so let's move on to our second step. I'm going to call our second step any conversions. All right, do you have any conversions? Well, in this case, yes, you actually do have a conversion. Okay, I need my units to be the same. I need my units of pressure to be the same. I need my units of volume to be the same. So here, my units of pressure are not the same, so I need to convert one of them. And if you remember from our last PowerPoint that we did, 1 atmosphere is equal to 760 millimeters of mercury. So I'm going to do a conversion there. Okay, so I'm going to, actually let's go to atmospheres, I think that's a little bit easier. I have 570 millimeters of mercury. To go to atmospheres, I need to do my dimensional analysis. Okay, so hopefully you remember how to do dimensional analysis. Okay, my units cancel. I'm left with atmospheres. And I'm going to go ahead and plug that in my calculator. It's 570 times 1 divided by 760. And you should get that it is 0.75 atmospheres. So now I'm good. I can say that's now 0.75 atmospheres. Okay. Now I'm going to move on to my third step, and I'm going to call my third step plug them in. So I'm going to take my values that I got up here, and I'm basically just going to plug them into my equation. Okay, so let me just kind of change colors here real quick. Alright, so I'm going to plug those into my equations. Well, we said volume 1 So I'm going to just write out what my formula is again. V1 times P1 equals V2 times P2. My volume 1 is 12.3. Okay. Whoops. And I should put my units, liters. Alright. Times my pressure 1, so that's 0.500 atmospheres. Okay. Is equal to my volume 2, which we don't know, so we're going to leave that as volume 2, times my pressure 2. We want to make sure my units are the same as my pressure 1. Okay, so now that I have that set up, I'm going to need to solve for V2. Okay, and that's my last step. My last step is to solve. Okay, to solve this, I need to multiply 12.3 times 0.5. Okay, so I'm going to plug that in my calculator. 12.3 times 0.5 is 6.15. Okay, equals V2 times 0.75 atmospheres. Okay, and the units on this, and I didn't write them, is liters times atmospheres. Okay, so we just want to make sure our units all kind of cancel out. Okay, and from there it's algebra. So I know a lot of y'all struggle with your algebra, with your math, but you know, from there that's kind of an expectation that you're going to be able to do that. To divide both sides by 0.75 atmospheres. Okay, my atmospheres cancel. I divide my 6.15 divided by 0.75, and the answer that I get is 8.2 liters. And that is your answer for the first Boyle's Law problem. Okay, so I'm going to go ahead and move on really quickly here. Hopefully you got all that. I'll give you a second just to kind of get it. Maybe you can pause it if you need to. But I'm going to go ahead and move on. Okay, and we're going to move to a second example problem, the last one we're going to do, and I'm going to kind of rush through this one a little bit more because you've seen what to do. Okay, so my first step, if you remember, my first step is to write out all of my values. Okay, I'm going to circle that first number I have. It's a pressure. So I'm going to say 3.0 atmospheres is pressure 1. Okay, I'm going to kind of go through here, and it says that my volume of a gas with the pressure of this increases from 1.5 to 6. Okay, so at a pressure, when I have my pressure at 3 atmospheres, my volume 1 is 1.5 liters, and it increases to 6.0 liters, so my volume 2. And my pressure 2 is what I'm going to be solving for. It wants to know what is the final pressure, or my pressure 2. Okay, my second step is to ask myself, do I have any conversions? Well, no. Both of my volumes are in liters, and I don't have to worry about whatever that is in because that's just what my answer is going to be in. Alright, so I can kind of just move on from there. My third step is to plug them in. So if you remember, V1 P1 equals V2 P2. So if I plug those in, it's 1.5 liters. Gosh, man. Times 3.0 atmospheres equals my second volume, which is 6.0 liters, times P2. And I move on to my last thing, which is solve. So now I just got to do my algebra. Multiply 1.5 times 3. Get 4.5 liters times atmospheres equals 6.0 liters times P2. Divide both sides by 6.0 liters. Liters cancel. I'm left with atmospheres, which is a unit of pressure, so I'm looking pretty good right now. And my answer that I get is 0.75. Okay, so I get 0.75 atmospheres. And one thing that I would kind of use when I'm doing these types of problems is after I've finished, I would say, does my answer make sense? Okay? In this case, my volume increased, and it actually increased by 4 times. My volume increases, what does my pressure got to do? It's got to decrease. Okay, did my pressure decrease? Yes, so I'm looking good. 0.75 atmospheres. So I think we're good with Boyle's Law.